This is Chapter 8, Sections 2 and 3 together, and we're covering this in two different parts. So this will be Part A today, and then we'll do Part B tomorrow. But again, Chapter 8, Sections 2 and 3, this is Part A. There are 5 types of chemical reactions that we will talk about, and we'll talk about the first 3 today. The first one we're going to talk about is combustion. And we just finished up balancing equations, and on our balancing equations worksheet, we briefly mentioned some combustion type equations that we have already seen, and you looked at them as far as a hydrocarbon and oxygen creating carbon dioxide and water. And those are a significant amount of combustion reactions, but we'll talk about a couple different types and what you have to have going on. But again, when you're doing types of reactions, and if we're going by state standards say that of these 5 reactions I give you, if I give you the reactants and tell you what type of reaction this is, then you should be able to tell me the products. So you should be able to predict products by the time we're finished, and you'll end up having some examples as far as homework and stuff where you get to practice this. So let's start with the first type, which is combustion. 2 things have to happen for you to have what is considered to be a combustion reaction. The first one, as it's shown here, is oxygen has to be a reactant. That is first and foremost, is oxygen has to be a reactant. So number 1, oxygen has to be a reactant. And the second thing that you have to be considered combustion is a lot of heat and or light has to be produced or given off. Heat and light has to be produced or given off. So it's got to have a lot of energy involved with this type of reaction. So anytime you see in this PowerPoint A, B, C, and D, like you see A in here and B here, these are just generic. So if you see letters by themselves, that's going to be elements. If you see a couple letters together, those are compounds, but it's still very generic. You can have a compound reacting with oxygen to give you one or more products. And we'll try to keep this somewhat simple. So in the example that they're showing you here, you've got CH4, which is methane gas, reacting with oxygen to give you carbon dioxide and water. Now this is a traditional combustion reaction because I would classify CH4 as a hydrocarbon because that compound contains hydrogen and carbon. So that is a traditional hydrocarbon. We are reacting this in the presence of oxygen. For all of our combustion reactions that we will talk about, even though this happens in multiple steps and multiple mechanisms, we're not getting into that yet. We're just going to go from start to finish and not worry about what happens in between. But for all of the combustion problems that we will deal with, CO2 and water are always going to be the products if you have a hydrocarbon reacting with oxygen. So this is a traditional combustion problem. Then you would go back and you would balance this. You can see that this one is already balanced. Now, even though I'm telling you these are traditional combustion problems, and if you had to predict the products for a hydrocarbon and oxygen, real easy to predict, it's always CO2 and water. But if it's not a traditional combustion, say it's not a hydrocarbon with oxygen and it's something else, say like sodium and oxygen, how do you know that that is going to be considered combustion? Well, I want you to think. Think of what we've already talked about with Group 1 and Group 2 metals. Group 1 and Group 2 metals. Group 1 and Group 2 metals, remember we saw them that they were very reactive in water? Well, the same is going to hold true with oxygen. Your Group 1 and Group 1 metals especially, you're never going to find out in nature alone. They're always going to be in a compound with something else because they are highly reactive. So this isn't true with every metal. So when I look at sodium and oxygen, they create a metal oxide. So sodium and oxygen create a metal oxide, and this one also falls underneath combustion because it does carry on the two things that we said. Number one, oxygen is a reactant, and number two, in this case right here, a lot of energy is given off during this reaction. Okay? So again, we're basing this on past knowledge, things that we've talked about, but you do have a lot of energy given off in this reaction. And here in a little bit, we'll look at a metal reacting with oxygen that's not considered to be combustion. Okay, so again, think of past knowledge, things we've done maybe in lab, videos that you've seen, and try to apply that as we go through this. The next reaction they're going to show you, this one now is balanced, so the coefficients are 4, 1, and 2. And in this reaction, we have C3H8 and oxygen. Now, this was actually on your worksheet, but again, if I asked you to predict the products of this, I'm looking, C3H8 is classified as what type of compound? Hopefully you answered a hydrocarbon. So if you have a hydrocarbon reacting with oxygen, the products always have to be CO2, carbon dioxide, and water. CO2 and water. Once you predict these products, because that's an easy type of combustion reaction now, you would go back and you would balance this. So again, this one was on your worksheet. Once you balance it, the coefficients are 1, 5, 3, and 4. So again, this covers combustion reactions. You have an element or compound that has to react with oxygen, number 1, and has to give off a lot of energy, number 2, to be considered combustion. Our second type of reaction we're going to talk about today is synthesis. Synthesis is where you've got a combination of 2 or more substances to form a compound. The key to this is there is only one product. Only one product. So make a note of that. That is the key to synthesis reaction, is you can only have one product. If you have an element and they synthesize, they will create one product. That's pretty easy. If you have a compound and an element creating one product, that can be just a little bit harder. So let's move on to some examples of a synthesis reaction. In this reaction here, we see that hydrogen gas and chlorine gas are reacting to produce HCl gas. Now, I mean, if you were here with me in class, I would definitely be asking you, what's HCl? It is an acid, and that is hydrochloric acid. But notice that we have a gas reacting with a gas, which is going to produce a gas. So that is very, very common. Even though you can find hydrochloric acid in a solution with water in liquid form, here it's going to be a gas. So what you've got is you've got this tank of hydrogen, and you have a flask over here to the side. In that flask is chlorine gas, and chlorine gas is a yellowish color. And the hydrogen gas is going to move out of this valve, through this tube, come through the glass rod, and come out of the bottom. Now, that part where the hydrogen gas and the chlorine meet, notice there's a flame right there. And that flame is just saying it gives off a lot of energy whenever these two get together. But they do react together spontaneously, and it gives you hydrochloric acid, but it's going to be in a gas phase. Remember, hydrogen and chlorine are both diatomic elements, so when you see them by themselves here and here, they are in their diatomic state, but notice they're not in their diatomic state once they react, and they don't have to be in their diatomic state after they react with each other. So that's a synthesis reaction. Again, the key to synthesis is you only have one product for a synthesis reaction. Only one product. Now, let's talk about predicting that one product. If you have, let's say your two original elements that are going to combine, one's a metal and a nonmetal, then it's not going to be too awfully hard. If you have a metal and a nonmetal based on what we did in Chapter 7, combine those, you're going to get an ionic compound. So just look at charges, cross over charges if you need to, cross over charges if they don't cancel, and you'll get your ionic compound. But if I gave you two nonmetals, or a covalent compound and a nonmetal, and said they combine to produce one product, it could be much harder to tell. I like to think of the examples of where the different sugars are going to be made, sucrose and glucose and fructose, things like that. It's just a different combination of carbon, hydrogen, and oxygen. So for you, at this point, really hard to tell. So if I ever asked you to predict products, unless it was something real simple like the previous one, if I ever asked you to predict products for a synthesis reaction, it's probably going to be an ionic compound, like the one that's shown down here. So if I look at the one that's shown below, we have aluminum, that's a metal, and chlorine is a nonmetal. And you know whenever you have a metal and a nonmetal that make an ionic compound, and in this case it is one product, you're going to look at their charges. Aluminum has a 3+ charge. Chlorine has a 1- charge. So when you cross those over, you get Al1, Cl3. So pretty easy to predict that product. AlCl3. Once you predict the product, you'll be asked to go back and fill in the coefficients out front so that you can balance the equation. So ionic compounds, predicting that one product, not too bad. That finishes our second type. Let's look at one other. And this kind of goes back to the combustion that we were talking about. What if I gave you iron reacts with air, so we're going to say oxygen gas. And now that's a metal and a nonmetal. And I told you that it creates iron oxide. First off, you don't know which form of iron I'm talking about, so I'm going to go ahead and give it to you. This is iron 3 oxide, which is rust. So pretty common. You've seen rust before. You know what it is. But if I go back and I think about originally, we talked about combustion reactions. And in a combustion reaction, oxygen was a reactant, but a lot of energy had to be given off over here. So do I have a lot of energy given off in the formation of rust? Your answer should be no. I mean, whenever a car is rusting because it's exposed to the elements, it happens over a long period of time. You don't see little explosions or fireworks, a lot of energy given off from that. It's a slow process. Energy is involved, but it's much less than what happens in combustion. So for this reaction, even though oxygen is a reactant, it is considered synthesis, not combustion, because a lot of energy is not given off. So I wanted you to see the difference where oxygen can still be a reactant, but not necessarily considered a combustion reaction. Now let's go to our third type. And the third type of reaction we're going to talk about is called decomposition. Decomposition is just the opposite from synthesis, meaning instead of you having just one product, in this case you are only going to have one reactant. Decomposition means to decompose or break down. So if you only have one reactant, you're going to break it down into simpler substances. So they've taken compound AB and they've broken it apart into A and B. So some of these are pretty easy. We'll talk about trying to predict the products here, but others are going to be fairly hard, and I wouldn't give you a hard one during this course. So this example should be pretty easy. Even though it's a molecular compound, water, it's only composed of two elements, and those two elements are hydrogen and oxygen. Does anybody know what this process is called that water is undergoing to break down into hydrogen and oxygen? And I believe it's a homework question at some point too. I'm putting ELEC here. Electricity is being added. There's a wire right here connected. There's a wire right here connected. It's called electrolysis. And when water undergoes electrolysis, basically you're electrifying it. You're breaking it down into the hydrogen and oxygen gases that make it up. And notice, hydrogen and oxygen, when they are broken up from water, they're now in their diatomic state. So don't forget about the diatomic state. And those two test tubes that they have right here, they were completely filled with water, as well as the dish below is also completely filled with water. And there are little probes that are sticking up right here within the test tubes. So whenever the electrolysis starts in and they start separating the water into hydrogen and oxygen, the space you see there at the top of each of these is the gas that is being formed, and it pushes the liquid down, and you can see the gas that is there. Notice that oxygen is about half of what hydrogen is, but again, look at your coefficients. Oxygen is produced at half the rate that hydrogen is because hydrogen has a coefficient of 2 in front of it. So this is electrolysis, breaking apart a compound into simpler substances. So when we're looking at this, if you have a binary compound that is your reactant, if your reactant is a binary compound, the reactant itself, the products are just going to break into the elements themselves. So water is a binary compound, pretty easy. It breaks into hydrogen and oxygen. Now, if your reactants, this others right here, if your reactant has 3 or more elements to it, it can be much harder to tell what it's going to break down into. Much harder to tell what it's going to break down into. So I do want to go through some examples now of showing you, after we do a simple binary one, look at ones that are going to be harder to tell. KBr, that is one reactant that's going to break into its products through decomposition. There's only 2 elements, so it's going to break apart into the elements that it is, which is potassium and bromine. Now remember, look for diatomic elements. Is potassium diatomic? The answer is no. Is bromine diatomic? The answer is yes. So you do have to put a 2 there since bromine is all by itself. After you predict the products, then you're going to go back and you are going to balance the equation. And there it is balanced, 2, 2, and 1. Now we're going to go and look at some decompositions that are going to be a little tougher. You're probably going to see some of these in your homework. We're going to break it into 4 different parts. We're going to look at decomposition of metal carbonates first. And when we pick these metal carbonates, it's best if you stick with group 1 and group 2 metals as we go through these examples, because group 1 and group 2 metals only have one possible charge, and that'll just make it easier whenever we try to break those down. If you have a metal carbonate and it breaks down, it will break down into the metal oxide and carbon dioxide. So let's pick an example of our metal. I'm just picking stuff out of group 1 and group 2. So calcium carbonate is CaCO3. And again, I look at charges. Calcium's a 2 plus, carbonate's a 2 minus, so the charges cancel. That breaks down into the metal oxide, which is calcium oxide. Again, if I look at charges, calcium's a 2 plus, oxide's a 2 minus, the charges cancel in CO2. So I would go back and balance this equation, and this one happens to already be balanced. So that's the first type. Second type we're going to look at is decomposition of a metal hydroxide. When you decompose a metal hydroxide, it breaks down into, again, a metal oxide, and instead of CO2, it is water. So let's pick another one. In this case right here, well, we'll pick calcium again. Calcium has a 2 plus charge. When you pair it up with hydroxide, which is a 1 minus, crossover charges, you get CaOH2. When it breaks down, it'll break down into the metal oxide, which is calcium oxide again, and water. Third example. Decomposition of a metal chlorate. Metal chlorate. So when you break it down, you will get a metal chloride and oxygen gas. So let's stick with calcium again. So calcium chlorate. Chloride or chlorate itself is a 1 minus charge, so that is ClO3 when I cross over charges, 2. It's going to break down into the metal chloride, which is calcium chloride. Chloride has a 1 minus charge, so when I cross over charges, it's CaCl2, and then oxygen gas. So again, you can stick in any group 1 or group 2 metal. Again, all of these carbonates, hydroxide, chlorates, any of those are going to produce an ionic compound, so we're crossing over charges. If you get the metal oxide, metal chloride, those are ionic compounds. You have to cross over charges. So there's 3 examples of decomposition reactions that are more complicated. So let's look at one more type of decomposition, which is you trying to decompose an acid. So if I wanted to break down an acid, it is going to depend on the acid that you're breaking down. Let's look at a couple of examples. First off, water is definitely going to be a product. So water is produced here, and we will look at the other product here. In the example, let's look at carbonic acid, H2CO3. We already said water is produced, so the other part that is produced is going to come from the anion that makes up your acid. So out of that, that's the carbonate ion. The other part that is produced is going to be CO2, carbon dioxide. If we looked at sulfuric acid, H2SO4, again, water is going to be produced, but we're going to look at this part of the acid, which is your anion, and the part here that will be produced. Take off one of the oxygens since it went to water. You're left with SO3, sulfur trioxide. So notice in both cases, we took off one of the oxygens to make our first product. Take off one oxygen to make your first product, and the second product is always going to be water.